Get started. Sorry, I was a little slow getting ready. Who would like to offer a prayer for us? Thank you. Amen. Thank you. Before we get started, any comments about the devotional yesterday? Yes. Okay, so that comment was, it was a reminder to not just focus on school, but on other things, other creative things in the rest of life. Although I wouldn't say that being creative and school are totally separate, right? So being creative in school is also very, very nice. But yes, thank you. Any other comments about the devotional? Yes, Michelle.
I really liked all the artwork that she showed during it. And it was just kind of cool how she talked about how like these different artists would decide to like show like these harsh things while others would like show these simple, beautiful things, and they'd be in the same time period, but like they're just representing different things, but they're both arts and they mean a lot to people. And so
Yeah, very nice. Yeah, I mean, as someone that spends a lot of time reading nonfiction and thinking about nonfiction kind of things, it's really refreshing to see the thought that goes into art and the meaning that people put into it and get out of it. So I really enjoyed that. Okay, let's go ahead and start with these problems. So find the following determinants. There's three matrices there to take the determinants of. Notice, if you didn't pick this up from the reading and the videos, the straight lines on each side mean take the determinant. Notice they're not brackets, so there's straight lines on each side. So that's an action to do. So take the determinant. Whereas the matrix in number 2, it has a bracket on each side. That's a matrix, not saying do something. But the straight lines, kind of like absolute value kind of signs, they represent take the determinant of a matrix. So go ahead and find the determinant of those 3 matrices and then answer number 2. I'm going to put that.
okay.
Okay, let's go ahead and start talking about this. So you all know how to find the determinant of a 2x2, not so slick a method for finding determinants of higher orders. And in fact, they're pretty hard. Lots of computations when you get up to not even very high, large sizes. If you did the reading, you saw that finding the determinant in using the cofactor expansion method for a 50 by 50 would take longer than the universe has existed with current computers. So it's crazy, like how difficult this is. So, we use other methods. We don't use the cofactor expansion very much. We have to be smarter about it. So there is a trick for a 3x3, and this is the one. This is the method. Some of you may have seen this method before. The book does talk about it, but this only works for a 3x3. Okay, doesn't work for a 4x4 or a 5x5. You can't generalize this. Okay, even though I said that last semester, but still people were doing this on the exam with a 4x4. So it doesn't generalize. So this trick, you rewrite your first and second rows over here, and then you have 3 downward diagonals. You multiply those together. So 2, 0, 0 is 0. 1, 1, and a -3 is a -3. 5 times 3 times 1 is 15. And then you have 3 upward diagonals. You multiply. So a -3 times 0 is 5 times 5 is 0. 1, 1, and 2 is 2. 0, 3, and 1 is 0. And then you subtract the upper diagonals, add the downward diagonals, and that's your determinant. Okay, questions about this method? Okay, not that bad. Lots of work in your head, so, and just making sure you line up the numbers right to get the diagonals right. Okay, but the method we have to use for 4x4 and higher is cofactor expansion. At least until we get some rules about how row reductions impact, how row operations impact the determinant. And with this strategy, you can pick any row or column to do the expansion. So, so here the student picked the first row, most of you did. So 2, 1, 5. So any number, it's important to know that for any number, there is a sign associated with that number. Okay, the plus or minus. So it starts with plus up here in the upper left-hand corner, and it alternates checkerboard fashion. Okay, so we take our numbers, we multiply them by the sign. So we have to change the sign of this 1 here. That's why, or we're subtracting the ones with negative signs. And you multiply it by the determinant of the minor. So you eliminate the row and column that the 2 is in, and you get a 2x2 matrix, and you multiply by the determinant of that. And then you eliminate the row and column the 1 was in, and you get a new matrix. You find the determinant of that, and you find the determinant. You take the 5, eliminate the row and column, get this one, and then you find the determinants of those, and then you add up everything. Questions about this method? Philip?
Yeah, there was when I was in I was wondering, it's not really related to the determinant, but I noticed this was the way I learned how to do cross products. And I was wondering if there was some relation between cross products and determinant.
So the question is, there a relationship between cross products and determinant? I'm sure there is, but I can't think of one off the top of my head. But there is a, for those of you that have done cross products, you can see a connection because you actually, you use the determinant, strategy to find your vector in the cross product. So I mean, you use this method, and but yeah, we don't have time to talk about it now. So, but yeah, but a deeper connection, I don't know. Okay, so since we can choose any row or column to expand along, we may have chosen a different row or column over here. Like I kind of like this one here. Why might we pick that one? There's a 0. That's one less lower determinant that I have to find. So I could do a -1 times, if I eliminate that, the row and column that -1 is in, I get 3, 0, a -3, 1, and then I get a -1. So I'm assigning I'm making sure I'm getting the signs here, times the determinant. If I eliminate the row and column, I get 2, 1, 3, 5, and then I get 0 minus a -3, which is a +3, so I'm -3, and here I get 2 minus 15, so that's what, a -13, +13, so +13 minus 3 equals 10, okay? So since you can choose any row or column, doesn't matter, choose wisely, okay? So that can help to eliminate some computations and minimize errors. Okay, any questions about this? Okay, so let's go back to the thing. All right, how about the determinant of that second matrix, that 4x4 upper triangular matrix? What's the determinant? 15. Why is it 15? You can just multiply down the diagonal. So for triangular matrices, you just multiply down the diagonal. That's equivalent of expanding along this first column, which only has one number. Then expand in the minor. You expand along this column, and you just have the 5, and then you expand along this column, and you just have the 3, and then you have the 1. So you just get 1, 5, 3, 1. Just by choosing wisely about which column or row you're expanding along. So, but they did have a theorem in the reading that for a triangular matrix, you just multiplied down the diagonals. All right, how about the last one? What is the determinant of that last 4x4 matrix? 0. Why 0? We have a column of all zeros. So, so you can think about it this way: if you expand along the column of zeros, you get 0 times all of the lower level determinants. So you just get zeros. But there's another reason why this should be 0. Philip? It does have something to do with not being invertible. If a matrix has a column of zeros, it's a non-invertible matrix, and we already know that a non-invertible matrix has a determinant of 0. So any non-invertible matrix has a determinant of 0. So if you see that 2 columns or 2 rows are multiples of each other, then you automatically know the determinant's going to be 0. Okay. All right, what is C21? So it's the cofactor of the second row, first column entry. So the cofactor for C21, what is that? I didn't pick a very interesting one here, but 2, 1, 5, 3, 0, 1, a -3, 1, 0. So we're second column. So this is the 2 here, first row. So this is this is the entry we're talking about. What is the cofactor? Three. I hear a -3. -5. Any other options? Okay, talk to your neighbor, see if you guys can figure out what the cofactor, see if you can remember. Less about figuring it out, but I wrote the definition up on the board according to the book. I don't know if that's helpful or not for you, but you have to understand the notation. All right. Okay. Now what is, you've been able to talk. I threw up another thing up here for discussion. What do we think the cofactor C21 is of A here? $15? 0? 5? Did someone just say 45? Or was that, oh no? Negative 15? Do we have all possible multiples of 3 and 5 up here and with signs? Negative 3, negative 5, 5, 15. Yeah. We don't have negative 45. All right. So good thing we're talking about this. So, the cofactor is the sign multiplied by the determinant of the minor, multiplied by the minor. So the cofactor doesn't include the 3. Okay. So you would have 3 times the cofactor times 2, 1 when you're trying to expand. But that cofactor is 3 times the sign, which would be negative, times the determinant of the minor. So you eliminate this and this, and you get 1, 5, 1, 0, and you get 0, minus 5. So this is a minus 5, a minus 1, and 3. But this is the cofactor right here. That's 2, 1. Okay, so only this is the cofactor. So the cofactor is 5. So, okay. So this is called the minor right here. The minor of 2, 1, or the minor of the second row to first entry. So the cofactor doesn't include that value. So you have the value times its cofactor, the next value times its cofactor, the next value times its cofactor. And you do that along a row or a column, that's what the determinant equals. Okay? So I know some of you were able to do this fine, but we do need to understand the notation and the language here, because that's what's going to show up on the test. That's what other people are going to use, and they're going to expect you to know it. Okay? That's what we'll use in class. Okay. I think I've got a slide or two on that. Yeah, so the cofactor is the minor multiplied by its plus or minus sign. So here the minor, what's the minor of A23? You eliminate the second row, third column, and you get the 2, 1, negative 3, 1. The determinant of that is the minor. So, okay. All right. Let's do, oh, I forget. Let me drag this up. Okay, so one more task, one more problem here before we dive into some other stuff. Find the determinant by first doing some row/column reductions. So you should have read about how these impacted you. But so I would encourage you to talk to your neighbors, try to review or teach each other what happens when you swap two rows. How does that change the determinant? How does adding a multiple of one row to another change the determinant? How does multiplying a row by a non-zero constant change the determinant? Okay, and then use those to do some row reductions to that matrix up there to make it so you can easily find the determinant. So you might do a row reduction so you have a triangular matrix, right? And then you can just multiply down the diagonals. But as you do row reductions, you can change the determinant. You have to keep track of how you change the determinant so that you can still find the correct answer. So, suppose you were on an exam, before I turn you loose here, suppose you were on an exam where you had to know those three bottom things and you didn't know, you forgot them. What could you do?
Well, you could, like, let's say we wanted to find the determinant of it just normally, and you look at it and then swap the rows and get the determinant again and compare the two values.
Okay. Yeah, pick a simple example. Apply the processes and then find the determinants each one to see how it changes. So you're not stuck if you can't remember what these are. These are stuff you can figure out. Okay. Now remember what a cofactor is. Now that's kind of just shows you have to know what that is. Okay, you're not going to just figure out what a cofactor is, but you can figure out what swapping two rows does on two rows or columns. You can do column operations too, but you can figure out what swapping two rows does. Pick a nice 2x2 matrix, simple 2x2 matrix. Not too simple, otherwise, if it comes out 0, it's not going to help you very much, right? But pick a 2x2 matrix, find the determinant, swap two rows, find the determinant. You can see how it changes. So, okay, so let me turn you loose on this. Figure out those three things, and then start doing row reductions up there. All right. I started doing this up here. Let's go ahead and finish together. You may have done row operations differently than what I've done or that I'm going to do. So that's just fine. We know there's different row operations you can do. My goal in general is to just get it to be upper triangular. I've already got some zeros down here. And so I was just going to focus on doing row reduction to get it upper triangular, and then I can multiply the down the diagonal and then make adjustments. So the first thing I did was I swapped two rows. And how does that change the determinant? Changes the sign. So I multiplied this by a negative sign here so I can keep track of that. So I swapped it. Then I added this second row to the third row, and the second -2 times the second row times the third row. How do those change the determinant? They don't. Those are really nice operations. Okay. Be careful because sometimes some of you may have been like me, and sometimes to do a row operation, you might multiply one row by 2 and another one by 3 and then add them together. That will change the determinant. Here we're only multiplying one row by a constant and adding it to an already existing row. But sometimes we've got rows of things we've got like a -2 and a 3, as you're reading and you're like, oh, I want to get rid of this one. I'm going to multiply this one by 3 and this one by 2 and then add. That's different. That's not just multiplying one row by a constant and then adding. And this will change your determinant. Okay? So, yeah, Philip?
So I did the same operation you did, but in the last row I got -4 and 0. Isn't oh, never mind.
Yeah. All right. Way to catch that. Okay, so still, the determinant of this is still just this except for the sign change. But now I'm going to divide by 3 here. I'm going to divide this row by 3. How's that going to change the determinant? It's going to be 1/3. How am I going to adjust that out here? No. Yeah, that will be a mistake. This is if I write 1/1 here, I've made that thing small 3 times as small. I've got to multiply by 3 to make sure I get it back the same size, right? So 1, 1, 2, 3, 0, 5, 2, 1, 0, 0. Oops, 1, 1. So yeah, that's going to be a common mistake that people make. You're going to be like, oh, I'm going to double this row, or I'm going to divide by half, and you're going to write a half out here. No, if you multiply by a half, you need to write 2 over here because you made this. You cut this in half. You need to double it to get it back to stay the same. And then I can multiply this second row by 4 and add, which isn't going to change it. So 0 and 3. Nope. Multiply by 4. It's going to be 12 minus 11. Is that 11? No, I'm 1. Yeah, I'm 1. I was right. Okay, so multiply by 4 minus 1, I'm 3. Right? Yeah, okay. So now this is easy. This is an upper triangular. This is easy. Multiply down the diagonal. It's 15. But I have to multiply by the -3, so -45. Okay? So, okay, so questions about that? Yes?
So when you divided the one row by 3, the 0, 0, 3, 3.
Yep.
What I did instead, which I got the same answer, I was wondering if it's like a one-time thing, but I multiplied it by 4/3 and then added to the bottom row. Would that be fine?
That's fine. So you kept your 3 in here. Yeah, that's just fine. So you kept the 3, 3 and multiplied by 4/3. That's just fine. Yep. So nice. You can also think about this 3 as you pulled out a 3. You factored out a 3 from that line. Some students like to think about it that way. So, yes.
I want to point out one thing. I just took a basic matrix 2 by 2 to determine So I have like the matrix 1, 2, 3, 4, and I multiply the top row by 2, and I got the determinant, it doubled, the determinant doubled.
That's right.
Oh,
Yeah, so it should have done, because you didn't multiply by that line and add it to another one. You just multiplied by that line. So if you take a line, if you take a row or a column and you multiply it by a non-zero constant, it's going to change the determinant by whatever you multiplied by.
what is it you're saying up here? It's like we had 3, 3 right there, and you're saying we're multiplied by 1/3.
Yeah, I multiplied this row by 1/3.
Yeah.
So I lowered the determinant by, this is going to be 1/3 as big. So I have to adjust for that. So that's why I multiplied by 3.
Yeah, so then in my example, when we have 1, 2, 3, 4, and I multiply the first row by 2, that becomes 2, 4, 3, 4. The determinant of the 1, 2, 3, 4 is -2, but the determinant of the other one is -4.
Right, so you're going to have to multiply this by 2. The determinant of this by 2, so to be the same. Yep. Yeah. So, okay. Or you can cut this in half, this one in half, and you can do 1/2 of this. Is that, so either way, those. Okay, good questions. So what does the determinant represent? Okay, so we're finding this. I am amazed that the book doesn't even talk about this, because this is like the easiest way to talk about it. I've alluded to this before in R2, but if you think of the rows or the columns, the vectors in Rn, then the determinant gives you this area. So if you have 2, if you're in R2, then you have this parallelogram. It'll give you the area of this parallelogram. If you have 3 vectors in R3, then it will give you the volume of this. This is called a parallelepiped. Okay. If you have 4, it'll give you a hypervolume. Okay. And it's kind of amazing that the formulas for those you'd think would be more complex, especially for the area one, but they're not. So here we have 2 vectors. The vectors are A, B. So notice I go over A and I go up B. So B's right here. So this is the vector AB. And this is the vector CD. I go over C this way, right? And I go up D. So these are my 2 vectors. And the question is, how much area is there here? Well, if you color these triangles and slide them, so if you slide this, slide the green down, slide this orange over, then you get a rectangle. And the rectangle is just A times D. But the rectangle includes more than just this area. Like the white area is this plus this little rectangle here. So to get the area, if we just want the area of this parallelogram, then we can take this area and subtract this area. And of course, that is AD minus BC. So if I were to give this problem to you, you guys would have started like dropping perpendiculars and using like length, square root. You're going to be doing the Pythagorean theorem in there, trying to figure out all these lengths. Super simple if you think about it the right way. So it represents that area in R2, or a volume in R3, or a hypervolume in higher dimensions. Okay. So here's a little thing. Has these shapes, it moves around, they move the shapes around, and in one configuration, they have an extra square. And in the other configuration, they lose the square. The shapes are exactly the same size. They don't change the shapes when they move them around. The upper corner is still here. This right triangle, the right corner is still there. This corner is still right there. So where in the world does that extra square come from? Any ideas? What is going on here? I guess nothing's going on. Okay, let's move on. No, we need to figure this out. Any ideas? It does. Yeah, so it calculates the area. So here it's 51.5 if you find the area of each of those. Here it's 52.5 because you have the area of each of the colored ones plus that one square right here. So, but how can it be bigger? Yes?
I have no idea, but I'm gonna take a long shot and say they're moving the shapes around kind of like maybe doing row operations and the extra squares coming in because it's like
I like the connection, and there might be something that a way to connect it that way, but I don't know if it's that strong of connection. So, yeah. Other ideas? I'm going to zoom in. Did they give something away? All right. What does that show? What? Is that you, Cambria? It's not perfectly on a line. So I can do the same thing up here. You zoom in there. So this isn't a triangle. This is a quadrilateral. If you connect this point to this point, it doesn't go through this point or this point. So right there, it's a little bit concave in. Right here, it's a little bit concave out. Okay? So just very subtle. And how much difference is there? Well, let's use the math. So the blue, the larger blue triangle, bluish, purplish triangle. Oh, I need it up for a second. Okay. So it's a 5 by 8. So we'll do 8 by. It's a 5 by 8 triangle. 8 by, yeah, 8 over 5 up. The smaller green, what is that? 5 by 3. Okay. So if I do a 5-8 and a 5-3, they're not. This 5-8 is not a scale of 3-5, right? But they're kind of close. So there's going to be this really small parallelogram here. It's really thin parallelogram there. So we can calculate how much area is in there. Oops. It's not a bracket. Okay. So what is this parallelogram going to be between those two vectors? 25 minus 24 equals 1. So if we drew the straight line to make it a triangle, one of them is a half a unit too small and one is a half a unit too big. And so when it's poked out, I'm exaggerating here, but when it's poked out here, then it's 1 unit larger than the other one, and that's why they can put 1 unit square there. So, okay. You can make these numbers are actually from the Fibonacci sequence, and you can make ones that are even harder to find. And the slope that they approach, the ratio of 5 over 3, 8 over 5, if you guys know the Fibonacci sequence, 13 over 8. Right, this slope, do you guys know what it approaches? It's the golden ratio. So, yeah. Okay. So let's go back to one more question for you to talk to your neighbor about. So if the determinant represents the n-dimensional hypervolume of n vector edges, explain to your neighbor why n linearly dependent columns or row vectors, so linearly dependent in Rn. So you have a square matrix, but the rows or columns are linearly dependent. Why does the determinant have to be 0? So do you have an area slash volume or slash hypervolume argument why it has to be 0? So talk to your neighbor. All right. Yeah, so one of the, I didn't get to many, I only got to one group, but that group said, in 2 dimensions, if you have linearly dependent rows or columns, then the vectors are on the same line, and you can't have an area if they're on the same line. In 3 dimensions, if they're linearly dependent, you would span at most a plane, but still maybe a line, right? But if you're, how much area does a plane hold? I'm sorry, not area. How much volume is there in a plane? 0. You have to have 3 dimensions. You're only down to two dimensions. So there is a volume argument, area and volume argument on why the determinant has to be 0 of a non-invertible matrix. So, all right, have a great day.